All right, so a couple of announcements. So far in the first 4 labs of the class, we haven't needed the laboratory textbook, the Kelton textbook, because we haven't been working with ARENA directly, and that textbook is really focused on applying discrete event system simulation to ARENA. On lab 5, which is the lab I think we start next week, we start seeing ARENA. So normally if you were coming to labs in person, then I'd want to make sure you have access to the lab textbook during the lab. But here, because I've provided the textbook online, it's a little less of a warning, but there's still stuff in the slides here. But basically means that that the next labs from here on out are usually going to be some modification of an exercise that was originally dreamed up by Kelton. So the labs, there'll still be a sort of a lab lecture where I'll talk a little bit and kind of open up and introduce the labs. But then in most of the lab experience, we'll point to a particular exercise that was started by Kelton, and then I might ask you to do a few things a little bit differently. But the bulk of it will have come out of that text. And part of the reason we do that is so you can also see the supporting materials that are within that. And so if you have additional questions about, well, what is this thing that I just did in ARENA? It wasn't quite as clear to me. Then the textbook can provide additional assistance. And of course, you can also ask me or the TA. We're both familiar with this platform. So we start seeing ARENA pop up in the lab, starting with lab 5. Homework B1 solutions are available on Canvas. So if you want to sort of see if your hand simulation turned out okay, then you can go and check out those solutions. And I believe the grader has graded all of those, but then now the way he did the grading is he graded all of the normal credit first and then went back and is grading the bonus credit. So you may not have gotten points for your bonus, even though you turned into the bonus, but then that will get revised as he goes through and grades all of those. And I think he might already be done with that. I have to confirm with him, but I know he's been feverishly running through those. So that's great. And then there are these Canvas activities that are always available. Again, not meant to be major pressure on you. I know you guys have got a lot on your plates already, but these Canvas activities are there to hopefully provide you unit by unit practice over what we did the previous units and what's coming up in the next units. And there's a heavy drop policy there. So I think there's only like 11 of these Canvas activities and we drop like the lowest 7. So if you've got other things that you'd like to prioritize, it makes sense to not worry about those, but if you are looking for that extra assistance, then they're there. The homework C2 is available on Canvas. It's a homework that is named after Unit C, but it really comes from the stuff that we're starting to talk about now. I kind of accelerated the schedule for the content in these homeworks because this is stuff that I want you to see on the midterm. So in order for you to get enough time to have practice with them and then also have time with the solution sets, I had to make sure that you started the homeworks kind of soon enough. And so this homework is on random number generation. You can read ahead a little bit in the textbook, or I've provided some additional help right underneath the homework there on Canvas. But we won't formally see this stuff in lecture for I think maybe at least one more lecture. But I think some people have already turned it in. I think it should be pretty straightforward for you to start working on. So that is due on the day of lecture D2, which is actually the next lecture. So that's Tuesday's lecture. So a clarification in case you've never seen this modulus before, it talks about this in the book, but A mod B just means what is the remainder when you divide A by B. So it's kind of like thinking about A divided by B, but instead of getting the quotient out, you get the remainder out. So as an example, if I were to do 5 mod 3, then I would get a 2 out because 3 goes into 5 once and there's 2 left over. So that's what mod means. It means modulus or modulo. So, and then for the homework, make sure to show your work. And so for question 1, it's very repeated. So you'll kind of plug things into a formula for the first part. And then you'll end up taking the number you get out of that first part and plugging it back into the same formula, and you do that like 5 times. Well, just show us the formulas. For question 2, you're doing a statistical test, and that test requires a little bit of arithmetic and a number of different steps to populate a kind of a table. And you don't have to show me necessarily the formulas you do for every cell of that table, because the formulas are going to be the same. But kind of following what the book does in, say, the header of that table, or the header row or header columns of that table, you can put the formula for the cells that follow it. And so if you look at the examples that I talk about, actually, if you just open up the homework exercise, on question 2, I say, you may want to look at exercises, whatever, 7.6 and 7.7. If you take a look at, or I'm sorry, examples 7.6 and 7.7, if you take a look at those in the book, you'll see an example of what I mean. So one of these tables where the formulas are kind of in the headers of the table. So you don't have to actually show me the formulas for every single calculation, but I like to see an indication that kind of what went into those numbers. And that way, if your numbers don't quite line up, we can match them up to the formulas and say, oh, you flipped these two numbers or something like that. Okay. So then moving forward here, so homework D2 will be released soon. I need to update it from last year, so I need to change some numbers and some formulas and things like that. There's already some help on homework D2, and I will put maybe an additional solution set out there for homework D2 to give some additional examples. This homework D2, again, this is something that I want you to have practice with before you get to the midterm. So what I'm going to do for this is it will have a normal due date, but I'll just basically wipe out the late policy so that those extra days that are normally there for the late policy will just be extra time for you to turn it in. So it will be formally due on whatever date it will be due on Canvas, but then those 4 days that I usually leave the assignment open where you get deducted 20% per day, we'll just not do deductions. And so it effectively will be due 4 days later, but just to keep things formal, I'll still make the due date when it's actually due, and then just again relieve the late policy, and then that should give you extra time to work on that homework and plenty of time then to practice that, and still have a little bit of time for the solution sets to become available before the midterm review and the midterm. So lecture F is going to be a midterm review. So this is lecture D1. So basically there's this lecture, D1, there's D2, then there's E1 and E2, and then there's F. And that F will be the lecture before the midterm. So that lecture F is just going to be a day where we review all of the other lectures, or we take your questions on the content so far. And so the ICA, the Canvas activity that corresponds to that F, is also meant to be a midterm review. And so after E1 is submitted, then F will be released. And basically F is just going to randomly sample from all of the previous Canvas activities and throw in a couple of other questions that I've kind of tossed in there to make things a little more interesting. And so that is meant for you to try to do before the midterm review lecture to sort of help get you thinking about questions that you might want to ask during the midterm review lecture. And you can complete it multiple times, and the highest grade is recorded. So, so that's how we're prepping for the midterm. And then finally, the midterm will show up in the next lecture period, the period after lecture F. And that is, it's about 2.5 weeks away. It technically is during the normal class time. That's here for a normal period. But because it's going to be a Canvas assigned thing, then it'll be with Respondus, Lockdown Browser, plus Monitor. I'll put a little kind of like sample assignment out there that everybody will be required to do to make sure that Monitor is working for them. And what it's going to do, it's going to be a timed assignment on Canvas where you'll get the whole day to do it. So you won't come to class that day. So you could spend the class period taking it. Or whenever is convenient for you, you'll get the 75 minutes to take the midterm, but you can start it at any time, but once you start it, you'll get those 75 minutes. And then during that time, it's closed book, but you will get two-sided handwritten formula sheets that during the process of completing the midterm, you'll show to the camera and so on. And so that way we'll see the sheets. So it's very similar to what you would do in class, but it's been kind of modulated for on the screen. And I've actually in the past shifted this class to Scantron lectures. So Scantron midterms anyway. So it's actually a pretty, it would be very similar to what it is, like nearly identical to what you get in class, because it will be an auto-graded test. It'll just be administered through Canvas instead of through, you know, paper-based bubble sheets. Then, and this is something which I guess is abnormal for a lot of you, but about a week and a half later, there will be a midterm retake. And so this is a no-fault retake. So if you just don't want to take the midterm the first time, you can then take the retake after that. It is not the same test. It'll be the same length. It will go over the same content, and they'll be engineered to be the same difficulty, as close as I can be. But it won't be the same test. And so it'll be roughly the same format though, still on Canvas and everything like that, still during class period, which means again, you'll have a whole day that instead of coming to class that day, you'll have an option to taking the retake. If you don't want to take the retake, you don't have to. We take the highest grade from the two tests. So if you do better on the midterm and not on the retake, if you just don't take the retake, we'll take your midterm score, or vice versa. So no stress. You don't have to take both tests. You don't have to take the first. You don't have to take the second. It's up to you how you want to divide your time between those two. You can take the first, and then if you felt like you weren't really comfortable with the format, and now you kind of learn the format, then you can go ahead and take the second, and we'll take your highest score on the second, for example. In between those two, I will do my best. In fact, I think it should be pretty easy to release the not only the solution set for the first midterm, but your scores for the first midterm, because it should be auto-graded. So you should know how well you did on the first midterm. You should be able to see the solution set and use that for studying, and then you'll have all that time, because that's traditionally fall break, I think, is where this thing straddle. Then you'll have all that time to decide whether you want to take the retake. So I know that's a lot of administrative stuff, so I want to pause here. Are there any questions about that? Is it pretty clear what follows here between now and the midterm and the retake? Okay. Oh, I heard a microphone go off, I thought.
Oh yeah, sorry, real quick. So it says the midterm is like during normal class time, but did you say that like we can take it like at any time throughout the day?
Right. So, I mean, I try to reuse as much material as I can from semester to semester. And so this is just kind of my standard phrasing, you know, during normal class time. So that would be, so, you know, so for our class, we can basically say that instead of during normal class time, it's this modified version that I just kind of told you, but it's, so don't think of it as normal during class or during normal class time. I'm sorry, I meant to try to cross that out here. I don't know if it's going to let me. Yeah, okay. So screwed that up. So that's just my standard phrasing. So for this semester, don't view it as during normal class time. View it as that what I just said is, you know, you'll it's during a normal class duration, 75 minutes. But you can start it anytime the day that it's scheduled for. And the day it's scheduled for is on the Canvas calendar. And so if we're counting ahead, I think it's like 2.5 weeks from now.
Okay, that makes sense. Thank you.
Mm-hmm. Any other questions, clarifications? All right, okay. Again, competitions out there. I've been getting emails asking me to remind students about this. The registration is the end of the month for the arena competition. Arena, you'll start using it next week. You can download Arena. You can use it on the lab computers. If you've got physical access to the lab, you can also use it on the remote computers if you don't have physical access to the lab. And I'm told that the performance should be very similar. So that's that. If you don't like Arena, or if you'd like to try something in healthcare, you could try the FlexSim competition or one of the other competitions. Or you can totally ignore this and just go the normal route, which is you'll find your own system, you'll find a group, you'll choose to model it with Arena, you won't be submitting to a competition, and you'll just do normal final project. This is just meant to help spice up the final project for some of you that want an additional challenge or additional motivation. Then you've got this competition. So that's all the reason I brought it up. So any other questions? Okay. All right. So let's go into the new material here then. So we've been talking a lot about different types of modeling, and we've said that for most of this class, we're focusing on discrete event system simulation. And of course, the name of the class is Simulating Stochastic Systems. It is a class on stochastic simulation. And so these DES simulation models, these stochastic simulation models, are designed to capture realistic variation without having to build models where you get everything right. And so the idea here is we take a so-called stochastic approach, and stochastic comes from the Greek for guess or conjecture. And so rather than saying that the world is random, we say it is easier for us to model a variable world if we just assume, we make a guess that the world is random. We actually don't care if the world is random, but we know that if it is not random, it is far too complicated for us to come up with a good model for. So instead, we're going to just assume that the world is random and then try to come up with the best distribution that we can use to capture realistic variation. So if I look at inter-arrival times at an airport, which was kind of my running example, so to speak, running here, that with people arriving here in an hour, then rather than taking the kind of, boring 470 approach and saying that, well, we got 5 arrivals per hour, whatever the heck that means, then what we say is, well, we actually get we do get 5 arrivals on average per hour, but some hours it's 4, some hours it's 6, and the time in between those arrivals kind of varies. And so what we're going to do is we're going to say, well, let's simulate a time in between those arrivals. It'll sometimes be less than the average, and other times it will sometimes be more than the average. And if we're able to sort of roll a die and it tells us whether we're above average or below average, or how much above average or how much below average, then these die rolls, if we design the die correctly, will end up giving us variations in inter-arrival times that actually look pretty realistic. And we didn't have to come up with some crazy microscopic model of all the reasons why somebody would arrive at an airport at a different time, because it turns out that if we take the distribution of the actual arrival times in reality, then those distributions have a structure which we can represent probabilistically. And so that's what we're doing. So input modeling will be the process of actually coming up with those probabilistic models and using them to generate this variation. So you either view this as, we don't know enough about the deterministic system, so we're going to fake it and use a random system instead. Or another perspective is that you say that the uncertainty and complexity of the real world are themselves sources of randomness. So we can view randomness not as some fundamental thing, like a quantum mechanical thing. We can actually view randomness as being generated by uncertainty. In which case, if the real world is full of uncertainty, the real world is full of randomness. So when we add randomness in, it's not that we're coming up with a fudge factor. It turns out we're actually trying to mimic the real world, because the real world is random. So either your perspective is the real world is deterministic, but it's too complex for us to understand, and so we use randomness to make it easier, or your perspective is the real world is random, then either way you have an argument for why we should be putting randomness into our simulation models. And so that's what we are getting ramped up to do. But before we can do that, we need to understand what the heck randomness even is to begin with. And so that's where this unit fits, is making sure that we all have a good understanding of probabilistic models and into what the heck even probability is. So that's what we'll talk about today. This might seem like it's a rehash of things you saw back in 385 or maybe 380. I am going to try to dress it up a bit and make it a little more rigorous, so that you can start seeing some of the terms that like a professional would use when talking about probability. So to start out, probability theory is actually a branch of something called measure theory. And so in mathematics, there is kind of a larger field that is sort of related to things like all of the crazy different ways you can invent to do an integral. and it is called measure theory. And measure theory basically is an abstract area of mathematics that deals with problems that look like problems related to weight or mass. And so measure theory provides ways in which we can think about ways of allocating mass to things. And so this kind of cartoon here, this mu is what's called a measure in measure theory. And what a measure does in measure theory is it takes an object and it can weigh that object. You can basically apply a weight to it. And the way the measure is built, if you were to take that object and break it into parts, like are shown here on the right-hand side of the equation, then the measure of the parts should add, when you add all those measures up together, it should add up to the measure of the whole. It doesn't sound like that's that exciting, but it turns out that making this generalizable across a wide range of objects you could represent in mathematics is not trivial to do. And a subfield of that, as we'll see, is probability theory, where the weight corresponds to the probability you associate with something. And so just like if I were to assign weight to this green ball, okay, sometimes it disappears. If I assign weight to this green ball, if it weighs a certain amount, if I tear this green ball in half, I better have a notion of weight where if I weigh the pieces, they add up to the whole. Well, likewise, if I assign probability to an outcome and probability to another outcome, if I have an event which is either outcome, then that event better have double the probability. So if I have two mutually exclusive outcomes and then I define something as saying I'm willing to accept either one, then I better have properly defined my probability measure so that that new thing, which is the combination of those two outcomes, happens twice as often as each individual one. And so that's kind of where probability theory fits into there. So let's try to make it a little more concrete. So in probability theory and real kind of more rigorous probability theory, we have this term random variable. And a random variable is neither random nor a variable. A random variable is actually a function, a mapping. It maps from a space of outcomes to what we call a measurable space. And so outcomes are mutually exclusive results of an experiment. If you flip a coin, the coin comes up heads or tails. Well, it either can go up heads or it either can come up tails. So our sample space, our outcome space, is heads and tails. Now, when we actually build a probability distribution, we will probably put on our x-axis, not heads and tails, we'll probably put 0 and 1. So we need to associate each outcome with a number in order for us to then do something useful and mathematical with it. And the random variable is just the association of outcomes with numbers. So it's a function that takes outcomes in the real world and turns them into numbers in a space in which we can do mathematics on them. That's what a random variable is. It's just an organization of outcomes into numbers. So another example that I put up here is the number of coins landing heads up if I flip a bunch of coins. That is a random variable because in the real world, you just get coins that land. When you look down, you just see coins. But then you say, well, how am I going to model this probabilistically? And your first step is to say, well, how do I represent this outcome? That I had some coins turning up heads and sometimes turning up tails. And I make the decision that I'm going to model that as counting the number of ones that landed heads up. So I've now assigned an outcome to a numerical representation, number that turn up heads up. And under that numerical representation, I can now define things like probability distributions and all of that stuff. But I first need to make that mapping, and that's what a random variable does. Okay. So a random variable formally is usually written like this. So a random variable x is usually written as you get more and more sophisticated, you'll see it followed as if it is a function because it is. And it is a mapping between this omega here and usually the real numbers, but it doesn't have to be the real numbers. But in this class, it'll always be the real numbers. So this omega is our so-called sample space. That's the list of things that can actually happen in the real world, and the list of mutually exclusive things that can happen in the real world. It either is heads or tails. We either saw 4 heads on the table or 5 heads on the table, not both. The range of the random variable is the the set of numbers that are induced by taking all of the outcomes and mapping them to that real number space, that number space that we had there. So if we find out that after we map all of the outcomes, then we find out that the number of coins either goes from 0 to 10 because we only have 10 coins, then our range of the random variable is 0, 1, 2, all the way up through 10. So the range of a random variable is just the, I would say it's the representation of how many numerical outcomes you can get after you map them all through the random variable. So that's what we mean by the range of a random variable. So as a shorthand, even though you should always be thinking of a random variable as this mapping, we oftentimes drop the mapping symbol here, the functional definition, and we just call it X. But even though we call it X, it's not actually a variable, it's a function, it's a mapping. So it's a formal entity that's mapping outcomes to numbers. That's what a random variable is. All right, another term that we're going to use, and this is a little confusing, is event. This event is not the same event that we use in discrete event system simulation. So this is a different definition for event. It is totally unrelated to simulation, but it just happens to be the term that we use in probability theory. And an event in probability theory is a set of outcomes. So outcomes are mutually exclusive. When you put them into a set together, then the set of outcomes is an event. And so, so two events do not have to be mutually exclusive. They can overlap in which outcomes are in them. So I've got these examples here. So outcomes are like a six-sided die. So that's the experiment I ran. I rolled a six-sided die, and it shows me 4 dots. Well, that 4 dots, that's an outcome. That is a single thing that can happen that is mutually exclusive. It cannot happen while any of the other things that could possibly happen. Jeremy is the only student who shows up to class. So if I'm modeling who shows up to class, one of the outcomes is Jeremy shows up to class. That's an outcome. That is one of the things that could happen. Now, events could be, well, a six-sided die shows 4 dots. Well, that's an event that has one outcome in it. Or a six-sided die shows at least 4 dots. So 4, 5, and 6. I grouped them together into an event. Jeremy is the only student who shows up to class. That's a single outcome that I could put into an event, and that would be like a set with only one thing in it. Or Jeremy and possibly others. So at least Jeremy shows up to class. That is an event. It is not an outcome. So an event is a set of outcomes. Okay. Those are some 2 terms there. Now, the reason we define event is because we'll need to define these measures. Like I mentioned, a measure is a way to weigh things. And so we weigh things in terms of probability. But then you have to ask, what do we weigh? Do we weigh outcomes? Turns out that we don't weigh outcomes because we sometimes need to weigh outcomes together. And so just like, so this green ball, I could stretch it apart and have it pop into 2. But then I could also put it back together. Well, that's what you can do with events. So events are bundles of outcomes that allow us to take them apart and put them back together. And we weigh the bundles, we weigh the events. And so a probability is a scale that can weigh an event. So, so by a scale, I mean, it's something that I can, like, you put something on a scale. And so a probability here should ensure conservation of probability mass. And so if you weigh an event, so you weigh something that has 4 outcomes in it, if you then create 2 new events that are subsets of that event, then those should weigh less than that. And they, if you add them up right, they should all add up to the same weight you had at the first event, so long as there's no overlap in the sub-events that you created. So, so the weights of events are the sums of the constituent of outcomes or events inside them. The weights are all non-negative, they can be 0. And the weight of the sample space is 1. So the probability of omega, the probability of the whole sample space, is equal to 1. So something will happen. That's one way you can view that. All right, so are there questions about these terms? The difference between outcome, event, and then how events are the things we use in when we define probability. So an outcome could be that one of you has a question. An outcome could be that two of you have a question. An event would be that one or two of you have a question. And then I could say, what's the probability that one or two of you have a question? And that would be the sum of the probability that one of you has a question and the sum of the probability that exactly two of you have a question. So exactly one of you and exactly two of you, those are mutually exclusive. And you could say, but Ted, you know, I could have, you know, I rather than mapping my things onto exactly how many people have a question, I could have said, you know, well, maybe the person who has a question, maybe that's the outcome I want to map. And so at that point, we're talking about a different random variable. So different outcomes in real space can be mapped to different numerical spaces, and thus we'll have different probability measures. And so that's the whole role of a random variable, is that mapping. Okay. All right, so with that, we can have different types of random variables. We have a discrete random variable, which just means that the range can be written as a countable set of things. And so a discrete random variable is one which either has a finite set or a set that's infinite, but I can arrange, I can kind of put a whole number on each element that's in there. So I can count to infinity, but I can count them. And so, you know, so I hope that makes sense to you what I mean by countably infinite. So the number of, for example, the number of times cosmic radiation can intersect this coffee cup, that is a count. And that count is unbounded. It could go to infinity, right? You know, if this thing sits here for long enough, it could go to infinity. You know, cosmic rays, an infinite number of times cosmic rays hit the coffee cup could happen. But because we can count it, we can say 0, 1, 2, all the way up to infinity, that is still a discrete random variable. So just because it's infinite doesn't mean it's continuous. It just means we have to then ask what type of infinite it is. So either finite or countable is what we mean by discrete. And so I give the example down here, the number of jobs arriving when we get a job shop. That in principle could be infinite. So that's because it's a count, but we still view it as a discrete random variable because we can count it. So the range of X, we often write R sub X, and it will end up looking like a set like this one. For each element in X, we have these shorthands. And so rather than saying the probability that our random variable is equal to any particular outcome, we'll just use a small p, and then we'll put that outcome in there. And so that is a shorthand for the mass, and I'll get to the reason why I say the word mass, but that is a shorthand for this. So little p with an outcome in it is the equivalent of big PR, big X is equal to that outcome. It's just a shorthand we use. And this kind of comes back to the definition of a probability measure. The probability of any outcome is going to be greater than or equal to 0, and the sum of all of the probabilities across all of the mutually exclusive outcomes equals 1. So this little p function we call the probability mass function, PMF, and the collection of points of outcomes and their probabilities together we refer to as the discrete probability distribution of X. All right, so that's a discrete random variable, and we'll get to continuous as a contrast. But before we get that, then this is an example, the number of spots face up on a die after a toss. This is the range here. It's just a set 1 through 6. And we can assign a probability to each one of these outcomes. So that's what I've done here in this table. And I've said for you know, for one, let's say for this particular die, not for all die, but for this particular die, seeing 1 dot up after a toss maybe happens with a probability of 1/21. But seeing 6 die up for the toss maybe happens with a probability of 6/21. And so this is not a fair die. So this die, it's very rare to see only 1 dot, and it's much more common to see 6 dots. So when you look at this, this together, so this is this little p here is our probability mass function. And so when we look at this, it turns out that the numerators are kind of the most important thing, and the denominator 21 here just sort of happens naturally. It's a so-called normalization factor. Where does the 21 come from? Why do the denominators of this particular probability mass function have to all be 21 in this case? Does anybody have a guess for that? Like, all I'm really saying here is that the probability that I get 6 dots facing up is 6 times as likely than the probability I get 1 dot facing up. So, so why do I need all the denominators to be equal to 21? Why don't I just make this 1 through 6? If I do this 1 through 6, this will still be 6 times as likely as this one. And I'm seeing some questions come in, or some answers come in, so I'll wait a little bit here. It'll be time to think about that. All right, so far I've seen answers like it's the sum of 1 to 6. I see the number of dots on a die. And I'm guessing you mean the sum of the number of dots. So there's 6, well, I see you mean the sum of all the numbers, yeah, because each face. So again, it's the sum of 1 through 6. I see because they add up to 21. I see 21 is the size of the sample. I'm not sure what we mean with size there. Summation of the sample space. And then now I've got this here. So I feel like this is building and building and building. And I see these last couple of answers here, the probabilities have to add up to 1. You want to weigh each number accordingly to its probability. So those two kind of go together there. And so all of these answers are kind of getting at what I want you to see here. And that's that I want this kind of conservation of probability where all of the probabilities together have to add up to 1. And the only way that happens is if we take their kind of likelihoods and we normalize them so that we turn them into these probabilities where if I were to add up 1 over 21, 2 over 21, etc., then the sum of all of these things will add up to 1. And so that's all that we're kind of saying here, is that the sum of all these probabilities add up to 1. So if I weigh the sample space, and the sample space is everything that could possibly happen, I could get 1, 2, 3, all the way 6 up there. If I weigh the sample space, so if I take the event of all things that could possibly happen, that should be equal to a probability of 1. And so in order for that to happen, the probability of each event has to be scaled down. And so that's why they're scaled by 21, to guarantee that the total sample space adds up to 1. So you could imagine I could give you on a midterm something like that, where I'd say, I've got 3 outcomes, and the third outcome is twice as likely as the second outcome. The second outcome is twice as likely as the first outcome. Tell me the probability of the second outcome. And so you could imagine initially just picking arbitrarily that, all right, well, I'm going to say the first outcome gets a probability, gets a candidate probability of 1. And because the second outcome is twice as likely, I'll give it a candidate probability of 2. Because the third outcome is twice as likely as the second, I'll give it a candidate probability of 4. And then so then this 1, 2, and 4, well, if I add those up together, that's a 7. Well, that means I need to divide them all by 7 in order to guarantee that my probabilities add up to 1. So, so that's 2 ways you can think about probability: is how do they relate to each other? That's kind of like a likelihood ratio type of thing. And then I need to make sure they're normalized properly so the sample spaces adds up to 1, and that's where these 21s come from. All right, so I might want to plot that. And so if I plot that thing here, then I get my discrete probability distribution, which is just the set of points where on the x-axis here, I've got the outcomes, and on the y-axis here, I've got the probabilities. And so you can see those pairs represented down here in this table as well. Each one of these funny things that has these pins that kind of have a pinhead within this long pin down here, has a fancy name in mathematics. It's called a Dirac delta measure. So I can put that in the chat if anybody is interested. I think I've probably got a slide here which actually says that, and maybe a little bit later. And so it's not arbitrary that we draw a dot with a little line that comes down on it here. That is a way of indicating to a measure theorist or to a probability theorist that you actually put a chunk of mass on a single point, because when we get to continuous variables, then we'll find out that they have no mass on individual points. They only acquire mass by integrating over ranges of points. But in discrete outcomes, you do put an individual mass on an individual point. And we indicate that by plotting it this way, by putting a little pinhead with a line down from it like that. That's a so-called delta measure. It is a special type of measure which accumulates mass in one particular point. So if you've ever seen a probability mass function plotted this way, it's not purely a stylistic convention. That is really how we indicate that this is a mass function and not a so-called density function that we're about to talk about. So we'll get into that next. Any questions about the discrete random variables? Okay. All right, so let's do a quick attendance question, and that will be, I'll put the URL. And the attendance question for today, or for this slide here, is going to be what is the probability that corresponds to the entire sample space, omega? So what is PR omega? So that should be a pretty easy one, pretty quick one. Just go to the URL, put that for question 1, leave it there until we're done. All right, so the other type of random variable that we have is the continuous random variable. And so this is a little harder to wrap your mind around, but if you keep in mind that probability falls into the same family of mathematics as mass and weight and these sorts of things, then we can finally have a way to kind of come to some intuitive understanding of what the hell probability density is. X is a continuous random variable if its range, so we now know what a range is. It's, if I take all my outcomes and I map them to numbers, if the things that I map them to, the numbers that correspond to each one of those outcomes in the real world, is an interval or a collection of intervals. So, if we're focused on the real line, so it's an interval that, square brackets A to B, it includes everything in between. So it's that fact that it includes a continuum there makes this a continuous random variable. And it can, again, be a set of intervals. So it can be a discrete set of intervals. It can be 3 intervals. But as long as you have one interval in there, and that interval, it's got a continuum in between it, that's why we refer to it as a continuous random variable. Probability here requires us to use an integral because there's no mass that's associated with individual points. There's only mass that are associated with intervals. And so I've represented this probability here. So I'm saying the probability that a random variable X is in between 2 real numbers A and B is the integral of this so-called probability density function, which we're going to talk about here in a second, from A to B. So it's the area underneath this density function from A to B. So what we're saying here is that there is probability associated with this region from A to B, but we're not associating probability with any point within the region. We're just associating probability with the region. You say, what does that even mean? There's weight to this green ball, right? This green ball weighs like something. If I were to take an infinitesimal slice of this green ball, which would cause all this ugly white goo to like spill out onto the table here, which I wouldn't do, but if I were to take an infinitesimally slice of this green ball, so that I just got a disc, a chip, like a potato chip of this green ball, but infinitesimally small, the weight of that infinitesimally small slice of this green ball would be 0. And so it doesn't make any sense to ask for the weight of objects in the real world at infinitesimally small points, because they don't weigh anything. They acquire weight by existing in intervals. The ball weighs something because it takes up a volume of space. I need a volume before I can assign a weight. And likewise with probability, with continuous variables, I need a range before I can give them a weight. And that's what the probability density function does, is you can say, okay, yeah, Ted, this green ball, maybe that slice, that potato chip slice of the green ball you took out of there doesn't weigh anything, but certainly it has a density. I took a mechanics class, I took a statics class or whatever, and in that class, we talked about the density of the ball, and that there's still density at every point, even though there's not weight at every point. And that's exactly what's going on with probability, is that we're saying that even though individual points in the continuum don't have a probability, they don't have a weight associated with them, they do have a density. And that density kind of represents the marginal probability you add to an existing volume if you start moving this direction in the continuum. So we'll see kind of more examples of that as we go on here. So this probability density function, again, you should think of it like density of a table or density of a ball or density of a coffee cup. And it has all the properties we'd expect of density. And so in density, you don't ever have a negative density. So densities here are always greater than 0. And if the outcome is not in the range of the random variable, then the density is equal to 0. And then it also is the case that if I integrate over the density, I then get exactly equal to 1. So that's the same thing as saying that if I were to know the density at every single point in this green ball, and I took a volume integral, then I would get the weight of the ball. Well, it's the same thing here. If I know the density of every point in the sample space, then the weight of the sample space would be the integral under that density, in that volume. And that comes from basically multiplying the densities by the volumes at each infinitesimal little point. Like you have a tiny little volume and you multiply it by the density next to that volume, and you add all those things up together and you get the weight of the volume. The thing that density then differs from probability is the same way that density differs from weight in real life. Densities can be greater than 1. So this is something you need to get into your heads, because this is an easy thing to get wrong. You're going to see probability densities that are 500. And you're going to say, how could a probability density be 500? Probabilities are bounded above by 1. You can't have a probability greater than 1. So how the heck do you have a probability density that's 500? It's the same way as saying that the probability density of or the weight, I'll say the density in terms of weight, can be extremely high at a point, but the surrounding weight of the object can be low. So you can have, this ball could have a really, really heavy marble inside the ball. The rest of the ball is light, but there is a tiny little marble that is super heavy, like the weight of the sun inside it. So if I were to hold it up and this ball was over here, it would just droop down. It's like you could have a super heavy ball inside this ball, and that would create a point in this ball that of extremely high density. And so numerically, that number for that density might be large. It might seem larger than the weight of the ball. But if I then take all of the densities together, the high densities and the low densities, then I get the weight of the ball. So the fundamental difference between density and weight is that they just have different units. Density is going to be like weight per volume. It's going to be like I get so many pounds of weight per every liter or something like that, for every volume that I add. And so it's a rate of, if I were to add a little bit more volume, how much more weight would I add, given that I've added that little bit more volume? Whereas weight doesn't have a per, it's not a rate, it's just pounds, it's just kilograms, it's just newtons, it's just a single unit, it's not a unit per. Probability density is so confusing because we don't represent it with units, but you should think about probability density as a rate. It is the amount of probability I pick up per unit, whatever my units are. So it might be per, if it's linear, like, it's whatever unit you associate with your outcomes in a line, or if it's a volume, it's whatever unit you associate with the volume that's in your outcome. So probability density is a rate. It's how much probability do I pick up if I add in a few more outcomes in this direction. It is not a probability itself. So densities can be greater than 1, even though the integral underneath the densities must be less than 1. So that's all I'm kind of saying down here, is that the integral under the density will be equal to 1, but any particular point in the density function can be greater than 1. That's really important to keep in mind. And then likewise, if we integrate from one point to itself, we get 0. And that's for the same reason why if I take an infinitesimally small slice of anything, the weight of that thing is going to be equal to 0. And that's because even though it has density, because I have not associated that density with any volume, because the slice that I've cut is so small, then that kills the density. So yeah, it could be the density of the sun, but if you sliced a slice so that it has 0 width, a 0 width piece of the sun has 0 mass. So even though the sun is really, really heavy, even though the sun is really, really dense, a 0 width slice of the sun has no weight. A 0 width slice of a probability density function has no probability. The probability of any individual point is equal to 0. If you throw a dart at a dartboard, the probability of hitting any individual point is equal to 0, even though the probability of hitting the whole dartboard might be 1. Or maybe it's 90% if you're like me and sometimes it strays. Okay, so there are questions about that, about what I mean by any of this stuff. I think I've got a graphical example here in the next slide or two anyway. All right, so as you're thinking about that, so graphically, I've got my interval over here between A and B, and I've got my point over here at point x0. And you can think of the entire density function as a block that has total weight 1. And the block, you can either view this as the density of the block, where the block is getting denser and heavier on one end, or if you think of this as a uniform density, you can think of this as the height of a block, and the block is just smaller on one end and larger on the other. So again, it tends to weigh more on this side over here. And so if you mentally model that way, then we know that the weight of this interval, that's like the probability of finding an outcome between A and B, and that's going to have weight. That is a sub-block on its own. You're going to feel that. But if you were to slice an infinitesimally small slice of the block, it's not going to have any weight. And that's the probability of an individual outcome. It has no probability. So the probability of one point is equal to 0. The probability of a range is the integral underneath the density. As that range gets smaller and smaller, then that probability goes to 0, regardless of what the density is. Okay, so an example, we might be modeling, input modeling, the lifetime of a device that inspects an aircraft wing, cracks in an aircraft wing. How long until that thing fails? The range of that random variable is anything from 0, it could fail this instant, to infinity, it could fail never. And it's not discretized. It could fail on any point in the continuum between 0 and infinity. It could be any non-negative value. Now, we might associate with it or look at the data and find that it corresponds to an exponential random variable. So it's one that looks like the one that's down here. And we might say that it has a mean of 2 years. So even though this particular one may not ever fail, the next one I buy might fail pretty quickly. And if I were to take an ensemble of these devices and see how often they fail, then we would end up finding that they come from this exponential random variable. So this kind of describes across the ensemble of devices sold by the device company, this is how often they might fail. And so I might then ask, well, okay, if on average they fail every 2 years, and I don't know how long it's going to take for this one to fail, what's the probability that it's going to fail between years 3 and 4? I want to make sure, do I really need a redundancy ready for years 3 and 4 so that it's on the shelf, and when this thing fails, I can just go to my redundancy. And so I can calculate that by taking the integral underneath this probability density function. So the density function might go above 1, but the area underneath the curve will not ever go above 1 because the area underneath the whole curve is equal to 1. So these sub areas are going to be less than 1. And so I just take an integral underneath the curve from 3 to 4, where I plug in my probability density function, and there I go. So this particular density function tops off at 1/2. So we don't have that issue, but the exponential could, if this had a very different average, then this thing could very easily peak higher than 1. So, so then, So that's fine. That's how we calculate it. So, so then you might say, well, you know, what does an average even mean in terms of this weight description here? And we'll get to that here in a second. That's kind of our next thing. But I want you to stare at this as we're about to describe this thing and kind of imagine where a block that was shaped this way, or how a block shaped this shape. If you were to go and cut out a piece of, you know, a piece of wood that would otherwise be homogeneous density, but it would be thin on one end and peaked on the other end, and then you tried to balance it on your finger, where would you put that block to get it to balance? And I just want you to think about that. Where would you put this block on your finger to get it to balance? And then think about that as we discuss the next topic, which are these distribution functions, and then ultimately we'll talk about moments and means. And so we'll get to that in a second. All right, so we have these random variables. Are there any questions about what I mean by continuous random variables, discrete random variables, the difference between them? Pretty clear, hopefully all review. Just want to make sure everybody's on the same page before we move on to more exotic things in the next couple of lectures. All right, so in this class, the CDF, the cumulative distribution function, is going to be super important. More important than the mass function and the density function. The CDF will be like the most important quantity to worry about here. So we want to make sure we understand what cumulative distribution functions are. So a CDF, typically denoted as capital F, sometimes capital F sub, and then the variable that it's talking about, like F sub X or F sub Y. So a cumulative distribution function represents the probabilities that your random variable is less than or equal to whatever number you put in the CDF. So it's a probability that something is less than that thing. So, and if for a discrete random variable, it's basically the sum of all of the outcomes that are ordered less than the focal outcome. So if I put an X in here, then I have to say how many outcomes are less than X. And then I take all those outcomes and I add up their probability mass functions, and that gives me the value of the CDF at that level of X. For a continuous random variable, it's just the integral from negative infinity up to that X of whatever the density function is. And so the properties, that convenient properties of CDFs, is that they are non-decreasing. So if you go from A to B, where B is larger than A, then you're not going to decrease. So you might stay the same and you might increase in your CDF. The limit of the CDF is equal to 1. And hopefully that makes sense. The limit is equal to 1. That as you take X is equal to infinity, then this is the probability that you will have an outcome less than this number that you're taking to infinity. Now, we know that as you take it to infinity, there are going to be more and more outcomes that are less than that number. So as X goes to infinity, eventually all of the outcomes will be less than that value of X. In which case, you're basically saying, what's the probability of all the outcomes? What's the probability of the sample space? And that's the reason why the CDF has a limiting value of 1. So CDFs tend to be very S-shaped. So if I were to go to my annotations here, a CDF is, I didn't mean to move that. If, so a CDF, if I were to, try this annotation again. So CDFs tend to be kind of S-shaped, where they start at, or they are 0 at negative infinity and 1 at positive infinity. And so this 0 here corresponds to that one. And that basically means if I go the other process where I take my barrier and I'm asking how many outcomes are less than that, if I take that barrier and I bring it to negative infinity, none of the outcomes are going to be less than that. So that's why the probability that outcomes are less than that goes to 0. And that's why all CDFs have this nice, usually S-shaped characteristic, where they start at 0 at negative infinity, they end up at 1 at positive infinity, regardless as if they're continuous or discrete or whatever, they always kind of have that shape. And that's a really important property. The other really important property with CDFs is that if I want to calculate the probability of a range, then rather than taking an integral, if I've given you the CDF on a midterm, for example, And if I give you that CDF, so I give you the function f, and I ask you for this probability, rather than you having to calculate an integral underneath a density function, you can just evaluate the CDF at the upper level and then subtract the CDF at the lower level, and you will end up getting the same thing you would get as if you integrated under the density function from A to B. That ends up being a super important and useful property. Okay, so those are our CDFs. So what have I done? There we go. All right, so our example for our die rolling example, this is the CDF for the die rolling. So you've got outcomes from 1 to 6, and every time you jump to a new outcome, your CDF jumps up by a little bit of amount. And if you look closely, then if you look closely here, then the magnitude of these jumps corresponds to the probability. And so you'll notice that this tiny little area here, this is, you know, a 1/21 jump, where this is a 6/21 jump. So this is, pardon my mouse writing, but this is supposed to be 6 divided by 21 there. And so all we're doing is we're stacking up all of the probabilities on top of each other, and that's why we get this this cumulative density function. All right, so that's the CDF for a discrete random variable, and then for a continuous random variable. So I've got this mouse wheel that's got like a super amount of inertia that I just turned off so that it doesn't keep doing that, and I apologize. So, oh, and then as a side note, if you were to draw a random number between 0 and 1, and then look at this CDF, and then map your random number that you drawed to wherever it intersects the CDF, if you were to do that over and over and over again, the outcomes that would come out would be according to the probability density or the probability mass function for the discrete random variable. So the CDF provides us a way to generate discrete random variables with any probability distribution we want. And that's something we cover in great detail in lecture E2. And then so the cumulative distribution function for a continuous random variable is going to look a lot smoother. It still starts at 0 and it ends in 1. And so this is the CDF for a exponential random variable. So the density is sloped the other way. It starts at 1/2 and then goes down and decays to 0. But if we add up everything underneath there, as so we're integrating underneath the density function, then we end up getting this rising function. So this is just the integral underneath the density function as you move from left to right. And so there you go. That's the cumulative distribution function. Then likewise, as we learn in lecture E2, if you were to draw a random number between 0 and 1, and you were to do this mapping where you bring that random number in sort of the wrong way, in from the y-axis, and then see where it maps on the x-axis, that process, if you to do over and over and over and over again, then histogram the results, then your results would be exponentially distributed. So the CDF provides us a way to go from a uniformly distributed random variable to between 0 and 1 and whatever distribution you want. And so if you have the CDF for a random variable, you can do this process to turn it, to draw samples from any other random variable, from that random variable using draws from 0 to 1. So you draw things uniformly from 0 to 1, which is on this side. You map them through the CDF back down to outcomes, and then those outcomes will be distributed according to whatever random variable is associated with that CDF. And so that's something, again, we'll cover in great detail in lecture E2. All right, any questions about CDFs, PDFs, variables, discrete, random? I think there's only one other thing that we need to cover here in the last 10 minutes of class. All right, so maybe I will do one other attendance question, and at least so far. And so in this attendance question here, I am asking you that if I have a random variable that has a range that is the interval from 2 to 3, what is the probability of the outcome 2.36? So if I were to give you a random variable x and its range was from 2 to 3, the whole interval 2 to 3, then my question to you is, what is the probability of the single outcome 2.36? All right. So the last thing that we need to talk about, just to get at our fundamentals here, is moments, or in this case, we'll start with the mean. So the expected value of a random variable is the center of mass of the distribution. So for a discrete random variable, it's just this formula here, which if you remember, if you took a statics class, again, if you took a mechanics class, then you can think of the P as the weight along a line. If you distribute weights along a line, you can think of P as the weight along a line and X as the distance from the end of the line. And so we're just multiplying distances by weights here. And that's what ends up giving us this formula here for the expected value. And for a continuous random variable, it's similar than that, but instead of using weights, we use densities. And so if you were to calculate the center of mass of a beam, you would need to know the density along that beam, and that would be this f of x. And if you multiply every density by the distance from the end of the beam, and then take that integral, then you end up getting the expected value, or the center of mass of the beam. And that's what where this formula comes from for the expected value continuous random variable. We will use these terms interchangeably: expected value, mean, and first moment. So that's another important term to know, the first moment. A moment, again, going back to your statics or your mechanics classes, if you take moments, moments are basically combinations of distances and masses. So if you're multiplying a distance by a mass, you're calculating a moment in mechanics. Well, it turns out mechanics inherits from measure theory the same way probability does. And so we use the same terms. And so we talk about a moment in probability. And the first moment is just the mean, or the expected value. So how do we interpret that? Well, if I were to take a probability density function, like this exponential density function here, there's the mean that I would calculate. That is the balance point. If I were to take a block of wood and I were to cut it into this shape, so let's say the block of wood had the same density everywhere, but it just is higher here. Or another way to view it is if I had a 2x4, but you managed to pack the 2x4 somehow, or a chunk of lumber, so that it was denser on one end than the other, and the density followed this pattern here, then this would be where you'd put your finger in order to balance it on your finger. So you just balance it up there, you balance on the mean. So I should be able to show you a graphical depiction of a probability density function or mass function, and you should be able to guess where the mean is without doing any calculations if you have an intuitive feeling of where things would balance. So you can use your mechanical intuition to predict where the mass is going to be. And that works with a discrete random variable as well. And I think I might have an image for that in the next lecture when we do our slides from before. But if you were to put a discrete random variable on here, it would be the same thing. These would be like kids sitting on a teeter-totter. Where do you put the fulcrum of the teeter-totter to keep the teeter-totter from tipping? That's going to be at the mean of the discrete distribution, where each kid is an outcome and each kid's weight is the probability associated with that outcome. So that's the first moment. We could also calculate other moments. And so the second moment, the third moment, and so on. And we just use the same formula, but the distance or the outcome ends up being raised to whatever the number that we put in that. So the nth moment just gets the same formulas, but we do x to the n instead of just x. So we got down here too. And we have those moments because there are other useful quantities like variance, which can be written in terms of moments. So the variance of a random variable is another term we associate with it, is the so-called second central moment. And so it is a moment that, so if you were to take the random variable and subtract off the mean, you generate a new random variable. And the second moment of that random variable is the variance of the original random variable. So we refer to this as the second central moment because it is equivalent to taking the second moment of a random variable that has then been centered around its mean. And so another term for second central moment is variance, and the square root of variance is standard deviation. And so conveniently, we have this really nice property that the variance of a random variable is just its second moment minus the square of its first moment, minus the square of its mean. So a lot of times it's easier to calculate the second moment and easier to calculate the mean, or you just have them available. And so if you need to calculate the variance, rather than going through the full variance formula, we can just use the second moment that we know and the first moment that we know, and we do this fancy subtraction, and then that ends up giving us the variance in a more simple way. So that's ends up being a convenient formula. All right, so any questions?
Hey, Professor.
Yes.
For that second attendance question, sorry to go back on it, are we assuming it's continuous or discrete?
That is supposed to be inferable by you, by the phrasing of the question. So
Okay.
that's part of the challenge.
Gotcha. Thank you.
Okay. Sure. All right. So in that case, where do we go from here? So next time, we're going to look at things like, you know, from how does queuing theory make use of these probabilistic models? What are the most common distributions that we will use in probability or in stochastic modeling? And why do we use them? When do we use an exponential? When is it right to use an exponential and wrong to use a uniform distribution and vice versa? When is it right to use a normal distribution, or when do I need to use a Weibull distribution instead? That's what we're getting into. And then what are the most common discrete distributions? So why do I have a Poisson distribution and I also have a negative binomial distribution? When do I use one and not the other, and vice versa? So that's what I want you to build up in this class, is an intuitive feeling for when to use distributions, and a vocabulary where you should be able to go to an expert and be able to just chat about negative binomials and Poissons and so on and so forth, as if they were tools that you could grab off a shelf. You know, do I need a Phillips head screwdriver, or do I need a slotted head screwdriver? Well, that should be, for us as industrial engineers, we may not worry so much about those types of tools, but we should worry about, do I need a normal distribution or do I need an exponential distribution, and why? And so it's obvious to somebody who's put things together when you need a slotted head screwdriver and not a Phillips, and vice versa. And it should be obvious to an industrial engineer when a normal distribution is the wrong choice, and you have to use a Rayleigh distribution instead, or something like that. So that's what you're going to start to build up here in this class. All right, so that is basically all I've got for you today. So what I'm going to do is give you the last attendance question, and I will open it up for questions and for the next couple of minutes, and that's all we've got. So the last attendance question I have here is, give me another name for the expected value of a random variable. I mentioned that we can call the expected value of a random variable a couple of different things. What is one of those things that we can call it? So what is another name for the expected value of a random variable? And I'll let that sit there. And if you have no questions, that's all I've got for you. So you can feel free to hop off. If you do have a question, happy to take one. I can hang around for a couple of minutes before I end the meeting. As a reminder, I have office hours today, I think at 4 o'clock, Mondays and Thursdays at 4. Any questions? Hope everybody is dealing with the isolation in useful ways. It's a beautiful day outside. It's kind of nice, I guess. All right, doesn't look like we've got any questions coming up here. So in that case, I hope everybody has a good weekend. Remember, there's a homework due on the day of, it's not due before Tuesday's lecture, but it's due Tuesday. So, and that homework is pretty straightforward, but you may need to read a little bit of the book to get ahead on that. But there's help that's posted right on the Canvas site, and then we'll end up covering that, I think, starting next week. All right. Have a good weekend, all.